Hello viewers, welcome back to BakoMaths, and today's lesson we'll be looking at how to augment matrices for systems of linear equations. And so if you have not subscribed to this channel, kindly subscribe for more updates. Let's get started. And so look at the meaning of augmented matrix. So augmented matrix is created by joining the columns of two matrices. So practically, if I have a matrix A to be equal to the element 1, 2, 3, and 4, and then if I have the matrix B to be equal to the element 2, 4, 6, 8, then to augment these two matrices, I'm just going to write it as into bracket A slash B. Now this slash sign or vertical line sign means that there are two matrices being combined, and so we continue by writing equal to. So join the two columns. So you consider matrix A. It has two columns, that is 1, 3, 2, 4. And so I can write them as 1, 2, 3, 4. And then the matrix B, that is its two columns are 2, 6, 4, 8. And so I have 2, 4, 6, and then 8. So basically that is how to augment matrices. Now we are going to chip in this idea in how to augment matrices for systems of linear equations. And so we are going to take our first example and then look at how to do that. So our first example, that is 4x1 plus 3x2 minus x3 is equal to -5. So let's label this one as equation 1. And then the next one as 2x1 minus 6x2 plus 2x3 is equal to 2. So let's name this one as equation 2. And then the last one, x1 plus 3x2 plus 4x3 is equal to 3. So let's name this one as equation 3. So now before we augment matrices for the systems of linear equations, we first have to change or write these systems of linear equations in matrix form. So with the help of the matrix equation formula, we can do that. So the matrix equation formula is giving us AX is equal to B. And so we know A to be the matrix of the coefficient. So we can write it as A is equal to matrix of the coefficient. And then we know X to be equal to matrix of the variable. So matrix of the variables. And then the last one, that is B, to be equal to the matrix of the constant. So matrix of the constant. So we can augment matrices for these systems of linear equations by using the matrix equation formula. So A says that matrix of the coefficient. So we can write it as so A to be equal to. Now the idea here is that we'd have to consider all the coefficients of the variables and then write them in matrix form. So when we consider x1, the variable x1, we are going to write the variables, we are going to write the coefficients of x1 in all the three equations. So when you look at equation 1, the coefficient of x1 is 4. That is 4. And so we can write it as 4 here. When we look at equation 2, the coefficient of x1 is 2. And so we write it as 2 here. When we look at equation 3, the coefficient of x1 is 1. And so we write it as 1. And so with this, we do same for equation for the variable x2. And so when we look at equation 1, the coefficient of x2 here is 3. So x2 is 3. So you can write x2 and write 3 here. And then when we look at equation 2, the coefficient of x2 is -6. And so we write -6 here. When we look at equation 3, the coefficient of x2 is 3. And so we write 3 here. And then the last one, that is x3. So the coefficient of x3 in equation 1 is -1, and so we write -1 here. And then the coefficient of x3 in equation 2 is 2, and so we write 2. Now the coefficient of x3 in equation 4 is 4, and so we write our 4 here. Now this is how we can write the matrix of the coefficient. Now the next one is to write the matrix of the variables, and so we can write the matrix of the variables as so x to be equal to, now we are going to write it in column form, and the reason we would explain later. And then we have the matrix of the constant to be equal to b. That is, now the matrix of the constant, they are -5, 2, and 3, and so you write it as such. So you have -5, 2, and 3. Now the reason why we are writing the matrix of the variables in column form is that when you look at the rule governing matrix multiplication, it says that for you to multiply two matrices, the number of columns of one matrix should be as the same as the number of rows of the other matrix. And so when you look at the matrix equation formula, we can see A and X are multiplying. And so for you to multiply these two matrices, like we said earlier, the number of columns of matrix A, how many columns do we see in matrix A? It's 3. That is 1, 2, and 3. And so we can see 3 columns. Now it should be as the same as the number of rows in the matrix X. So when you look at the matrix X, the number of rows here, they are 1. So horizontally 1, 2, 3. And so we can multiply these two matrices. And that's why we intend to write the matrix of the variables in column form. If you intend to write in row form, it will not comply to the rule governing matrix multiplication. So that is the idea behind why we are writing the matrix of the variables in column form. And so having changed the systems of linear equations into matrix form, what we are going to do here, or what we are going to do next, is to augment the matrices we've written. And so we are just going to consider the matrix A and B in the matrix augmentation, because leaving out the matrix of the variables, because after the matrix augmentation, we are going to use the process of Gaussian elimination or Gauss-Jordan elimination to solve for the augmented matrix. And that procedure will lead us to the solution of the variables. And that is why we don't include the matrix of the variables in the matrix augmentation. And so to augment matrix A and B, like we said earlier in our introduction, then we can write something as A. You can write something as A slash B to be equal to, now the matrix A is giving us 4, 3, -1, and we have 2, -6, and then 2, and then the last one, that is 1, 3, 4. And then we bring our vertical line indicating that two matrices has been combined or joined. And then the matrix B is giving us -5, 2, and then 3. So this is how we can augment matrices for systems of linear equations. And so we'll move on to our next example, that is example 2. And then in example 2, we have -2x plus y to be equal to -5. So we can also label this one as equation 1. And then we have 3x minus z to be equal to 2. So we can label this one as equation 2. And then the next one, 3y plus 2z to be equal to 3. And so we can label this one as equation 3. Now, the next step here is to write the matrices for these systems of linear equations. And so, like we said earlier, using the matrix equation formula, that is AS is equal to B, we know A to be equal to the matrix of the coefficient, and X to be equal to matrix of the variables, and B to be equal to matrix of the constant. And so with A, the matrix of the coefficient, and so when you take the coefficient X, It's not always going to be x1, x2, x3. Sometimes it can be x, y, and z. And so when we take x, the coefficient of x in equation 1 is -2. And so write it matrix A. The coefficient of x in equation 2 is 3. And so write it. And then the coefficient of x in equation 3 here is 0. And so since there is no value or variable in equation 3, we tend to write it as 0. And then we continue with y. And with y, we are going to have the coefficient of y in equation 1. The coefficient of y in equation 1 is 1. And the coefficient of y in equation 2 here, since there is no y variable or value here, it tends to be 0. And then the coefficient of y in equation 3 is 3. Move on to z. And then with z, the coefficient of z in, let's write this well, sorry. And so the coefficient of z in equation 1 is 0. Since there is no z value or variable here, is 0. The coefficient of z in equation 2 is -1. And the coefficient of z in equation 3 is 2. And so this is how we can write the matrix of the coefficient. And then as usual, the matrix of the variable, though we may not use it in our matrix augmentation, but we can write it as x, y, and z. And then we have the matrix of the constant b, that is equal to -5, 2, and 3. And so we can augment the matrix for the matrix we have derived. So with the matrix augmentation, then we can have something like into bracket a slash b to be equal to, we are just augmenting matrix a and b, and so you have -3, 1, 0, and we have 3, 0, -1, and we have 0, 3, 2. We bring our vertical line, then we bring our matrix b, that is -5, 2, and 3. And so that is how we can augment matrices for the systems of linear equation we see in equation 2. And so move on with our third example. And with our third example, we have 2x plus y minus z to be equal to 1. And so we can label this as equation 1. And so we have equation 1. And then 4x plus y to be equal to 2. And so this one has 2. And the last one, minus 2x plus 3y plus 2z to be equal to 3. We have this one as equation 3. So the first step, as usual, we can write the matrix equation formula, this one, and we emphatically know that A is the matrix of the coefficient. And so to write A as such, then we can have A to be equal to, this comprises of x, y, and z. And so x in equation 1, its coefficient is 2. X in equation 2, its coefficient is 4. X in equation 3, its coefficient is -2. When we come to y, y in equation 1, its coefficient is 1. Y in equation 2, its coefficient is 1. Y in equation 3, its coefficient is 3. Then we come to z. Z in equation 1, its coefficient is -1. Z in equation 2, its coefficient is 0. And z in equation 3, its coefficient is 2. And so we have our matrix equation. And so we can also write our matrix of the variables, though we may not use it. And so we have x to be equal to x, y, z. Fine. Then the last one, the matrix of the constant. And then the constant, we have 1, 2, and 3. This is how we write it. So to augment these matrices, then we have A slash B to be equal to, our matrix A is giving us 2, 1, -1, and we have 4, 1, 0, and we have -2, 3, and 2, slash Then the matrix B is given as 1, 2, 3. And so that is how we can augment matrices for this system of linear equation. And so we'll continue with our last example. And this last example, we have 6x1 plus 3x2 minus x3 to be equal to 1. And so we can call this one as equation 1 as usual. And have 2x1 minus 7x2 plus 2x3 to be equal to 2. Let's call this one to equation 2. And x1 plus 4x2 plus 4x3 is equal to 8. Let's call this one as equation 3. Now, with the matrix equation formula, AS is equal to B, we know what A stands for. A stands for the matrix of the coefficients. So when you consider A, you are going to have, so for x1, for x1, its coefficient here is 6 in equation 1. And then x1 coefficient in equation 2 is 2. S1 coefficient in equation 3 is 1. In the same way, when we go to x2 coefficient in equation 1 is 3. x2 coefficient in equation 2 is minus 7. x2 coefficient in equation 3 is 4. And then the last one, that is x3. And so x3 coefficient in equation 1 is minus 1. x3 coefficient in equation 2 is 2. x3 coefficient in equation 3 is 4. So this is the matrix of the coefficient. And so we can also write the matrix for the variables. That is, we have x1, x2, x3. And then also the matrix of the constant. And so we have B to be equal to 1, 2, 3. And so to augment these matrices, we have A into bracket A slash B. Then we have our matrix augmented as 6, 3, -1, 2, -7, 2. We have 1, 4, 4. We bring our vertical line in between those two matrices, and we have the matrix B as 1, 2, 3. So this is how we augment matrices for systems of linear equations. And so thanks for watching. Kindly like, comment, subscribe, and share. See you in our next video. BakoMaths, thinking beyond infinity.